All right. Thank you very much. Thank you all so much for having me here today. It's really great to be able to speak to so many people interested in glaciology and the icy parts of our world. And so I will just get started. And before I go too far, I just want to thank the long list of people who have been involved in this project so far, from many different universities across the United States and into Europe. And this list continues to grow as more people become involved in this project. So it's been really exciting as a young scientist to get to work with so many people who have so much expertise and knowledge about so many different parts of the Earth. And so it's just been just quite an honor to have that experience. So as we get started, I think it's always good to center ourselves in where we are in history right now. And being, I'm only about 32 years old, and I think that we are living in one of the most rapidly changing or uncertain or consequential times in human history. And of course, us as scientists who are interested in what's going on in the icy places of the planet are well aware that CO2 has been rapidly increasing year after year. And we have a good record of that from the Keeling curve. But I want to go back to the very beginning of the Keeling curve history, back in the late 50s and early 60s. And at that time, carbon dioxide is 315. And oh, I see that something is blocked on the screen. I will fix that right now for you. Sorry. There you go. That should work. And if we go back to that time in history, carbon dioxide wasn't this existential threat to us yet. Climate change was not that big threat. We had a different one, and that was that the Arctic was the closest path between the US and the USSR at the height of the Cold War. And this was the most direct path for intercontinental ballistic missiles that might have caused a nuclear strike. And so the fear of a long-range missile strike going across the, oh, I see what's blocking it, sorry. One second, everyone. So that's not, okay. Did that fix it?
No, it didn't.
It didn't?
It might in a second. Yeah, there we go.
There it is.
Okay,
There it is.
sorry. So, I have a dual screen setup going on where I can't see my large screen behind my little laptop. So I missed a window that was popped up. Sorry about that.
Well, we don't want to miss that scene from Dr. Strangelove.
Yeah, that's right. Okay, thanks for pointing that out. So the fear of nuclear war across the Arctic between the USSR and the United States led to a large military buildup in the far north. And in Greenland, in northwestern Greenland, it led to the building of the Thule ballistic missile early warning system. And about 100 miles from the Thule base, the US Army decided to build an experimental military base inside of the Greenland ice sheet. So next I'm going to show an old propaganda video from the US Army showing what this place was like.
On the top of the world, below the surface of a giant ice cap, a city is buried. Today, on the island of Greenland, as part of man's continuing efforts to master the secrets of survival in the Arctic, the United States Army has established an unprecedented nuclear-powered Arctic Research Center. Located in a wilderness of ice and snow, Camp Century is 150 miles from Thule, its nearest base of supply. This is an ideal Arctic laboratory. For more than 90% of Greenland is permanently frozen under a polar ice cap which covers all but a few coastal areas of the island. Camp Century is buried below the surface of this ice cap. Beneath it, the ice descends for 6,000 feet. In this remote setting, less than 800 miles from the North Pole, Camp Century is a symbol of man's unceasing struggle to conquer his environment, to increase his ability to live and fight if necessary under polar conditions. This is the story of Camp Century, the city under ice.
Okay, so Camp Century was a U.S. Army base that was built inside of the Greenland ice sheet to learn how to live in polar conditions and conduct scientific research. In reality, this may have been a front for Project Iceworm, a secret feasibility study to figure out if the U.S. Army could store nuclear weapons inside of the Greenland ice sheet. But this base was very publicly visible at the time through propaganda published in National Geographic, and it was also, the base itself was also powered by a small nuclear reactor that supplied electricity for the 100+ soldiers and technicians and scientists who lived and worked at the base. They even brought up Walter Cronkite, the famed newscaster from CBS, who has this 30-minute long film reel of him up at Camp Century, and he has this amazing quote at the end of his newscast: "Man brought his greatest scientific achievement, power from the atom, to the very top of the world, but can he live here? Can he stop the crushing force of the ageless ice?" And that's the way it was not, Walter Cronkite, because the Army soon realized that the snow and glacier ice in that part of Greenland was destructive through plastic deformation. And for example, they went back in the late 60s, only 5 years later, to see that these trenches that they had dug into the ice began to close in, kind of like the trash compactor scene in Star Wars, and that the nuclear reactor building was crushed from the high snowfall rates above. So they learned that ice sheets are in fact a terrible place to store nuclear weapons, and I'm glad that was what they realized. But a lasting legacy of Camp Century is that we realize that they're a great archive of paleoclimate data. So one of the projects that was going on to figure out if we could store nuclear weapons inside the ice sheet had to do with the fundamental behavior of ice itself. And those projects led to the collection of the very first ice core. So the Camp Century ice core was the first drilled through an ice sheet, and it really revolutionized our understanding of paleoclimate. Back in the late 1960s, Willie Dansgaard and others published this revolutionary paper that documented for the first time these really detailed changes in Earth's climate over the last 100,000 years or so. And so, I think about this as a glacial geologist, and thinking back to in the former part of the 20th century, that we could identify on land that things had changed a lot recently in Earth's history. But this sort of ice core record was the first time we could see in detail just how dynamic Earth's climate was during the last glacial period, and the warming that happened through the last deglaciation. So while the top of that ice core was revolutionary, they also did something revolutionary in that they made it all the way to the bottom. In the bottom of the ice sheet, they collected almost 16 meters of debris-laden or silty ice, and at the very bottom, 3.5 meters of frozen sediment. And to this day, that remains the thickest sequence of subglacial sediment recovered from Greenland. But the sediment at the bottom of the ice core was not thoroughly studied. It was sent to Copenhagen in the 90s, and then it's been misplaced and unstudied for decades. And so if we just think about this in terms of time, you know, this is back in the 60s, the ice core is completed. Dansgaard publishes his seminal paper in 1969. And then the last papers written about the basal materials from Camp Century were in the early 80s. And now they've been rediscovered a couple years ago. And so this is an amazing opportunity for us as scientists because there have been immense advances in the analytical techniques since the ice core was collected in 1966. You know, this ice core has been frozen longer than Dr. Evil was stuck up in space. So we can use analytical techniques that were unimaginable when the sediment was collected nearly 60 years ago. And so now I'm going to show basically a sequence of pictures of geologists and glaciologists admiring dirt. And here's Lyle Hansen and Chet Langway examining the basal sediment back in the late 60s, and Dorte Dahl Jensen in Copenhagen with the basal ice from Camp Century a couple of years ago. And I'll note that Dorte and J.P. Stephenson invited Paul Bierman and others, including George Schaefer, to come and figure out what we could do to understand this unique archive. And a couple of samples from the Camp Century sediment ended up at UVM, and here I am subsampling a bit of the exact same sediment that's shown here with Hansen and Langway almost 60 years ago. And what we are finding from the sediment has been really surprising. So the story of Camp Century isn't just the city under the ice, it's the ecosystem under the ice. And just as the largest picture conclusions that I'm going to talk about from our recent research is that we found fossil plants and biomolecules from ancient tundra from at least 2 ice-free events, once in the early Pleistocene and another in the last million years. And just as a teaser to hopefully convince you to watch the rest of the talk, I'm going to present some new data that gives us a little bit more of a refined age of the last time Camp Century was ice-free. All right, so we found twigs in frozen dirt from the last million years. Why does that matter? Well, this sediment is a time capsule from a less icy and warmer Greenland. And as humans continue to change our planet and warm its climate, could this be a view into our warmer future? And we are already seeing a greener and less icy Greenland because right now, warmer summers are causing Arctic greening, which is marked by increasing biomass and the migration of shrubs and forests into formerly tundra areas. And these changes have been complex, that some places have greened more than others, but ultimately these changes will have implications in the near future for changing the carbon budget as well as surface energy budgets across the Arctic that could trigger additional climate feedbacks.
Drew, you've still got a couple of small black boxes. I don't know whether they're easy to get rid of.
Is it near the top?
Yes, 2.
2? All right. I think one might actually be the
Zoom or something like that.
Zoom thing.
That's made it worse, actually.
That's made it worse.
That's better.
Okay. Is it just the very top?
I think it's fine. Yes.
Okay.
Yeah.
Thank you for letting me know. Okay. So then, of course, the other large change that's going on in Greenland is that the Greenland ice sheet is melting and losing mass year after year. And we are seeing within the era of satellite observation that the margins of the ice sheet are losing the most mass. And in particular, one of the most vulnerable areas of the Greenland ice sheet is in the northwest corner where Camp Century is. Of course, this means that in the near future, the implication is that we are going to have increasing contribution to sea level rise from Greenland within our lifetimes. So then the natural question to ask is, how will the Greenland ice sheet melt under future warming? And ice sheet models that consider different greenhouse gas emission scenarios are projecting that we could lose large portions of the Greenland ice sheet and contribute as much as 1 meter to 3.74 meters of sea level rise from Greenland by 2300, right? So what we want to understand is, how is Greenland going to change in the future? And to do that, we can look to the geologic past. And specifically, we want to ask a couple of questions. When and where did parts of the Greenland ice sheet melt away in the past? And what ecosystems emerged in Greenland under warmer and ice-free conditions? But there is a big complication. We have a giant ice sheet that is covering those landscapes that were formerly ice-free, and it has also eroded most of those sedimentary archives on the landmass itself that would provide a record of that. So we ultimately have a incomplete or fragmentary geologic record of the Greenland ice sheet. So we can look to other lines of evidence from around the Greenland ice sheet to understand its history within paleoclimate of the last several million years. And at the bottom of the screen, I'm showing a recent global mean sea level reconstruction, just as sort of like a global proxy for how changes in ice sheet volume have occurred in the last 8 million years. And one way that we can understand how the Greenland ice sheet has changed over this time period is to look at ice-wrapped debris that is transported by icebergs and left out into the deep ocean and deposited on the seafloor. And that tells us that the ice sheet first reached the coast. Marine terminating glaciers first reached the coast by at least 7.5 million years ago, and they began to erode the landscape. We see large pulses in ice-wrapped debris around 3.3 million years ago, and again at 2.6 million years ago, which marks the onset of a fully expanded Greenland ice sheet, somewhat similar to what we have today. Geophysical records offshore of Greenland can give us a reconstruction of how many different ice advances have occurred from the ice sheet in the past, like this really good one by Paul Knutz a couple of years ago. And we can also look to rare areas or along the fringes of the ice sheet where there are terrestrial sediments that contain plant fossils that tell us about what used to live on Greenland, including boreal forests, during past warm intervals. And then we can also look at sediment offshore and look at the pollen concentrations in that sediment to see what may have been living on Greenland during past warm periods or interglacials. And so from these different records, there are potential times when the Greenland ice sheet was smaller than it is today. The other way that we can understand this record is by looking at ice core basal materials. So ice core basal materials, which include silty ice, subglacial till or diamictin, and subglacial bedrock, are ultimately quite sparse in ice cores and challenging to recover, but they can contain paleoclimate data that is older than the overlying ice sheet. And so from a recent paper that we just published about Camp Century, we have the synthesis of all the different analyses that folks have applied to basal materials from ice cores in Greenland. And really, the important thing about basal materials in these ice cores is that they are the direct evidence from formerly ice-free landscapes. Geologic records, both offshore and beneath the ice sheet, point to a smaller Greenland ice sheet within the last 1.1 million years. Offshore, we see pollen concentrations, changes in ice-wrapped debris, changes in sediment composition, and changes in sea surface temperatures that suggest that the Greenland ice sheet may have been smaller or severely reduced during some of the middle Pleistocene interglacials like MIS 11, maybe 9, maybe 7, maybe 5. And then ice core basal materials suggest that the ice sheet is no older than 1 million years old, that there's no ice older than 1 million years old. There is DNA at the bottom of the die-3 core with that has the marks of boreal forest and sort of uncertain age constraints. The silty ice at grip is 950 or 970,000 years old. But at GISP2, the subglacial bedrock requires exposure and therefore ice-free conditions within the last 1.1 million years. Meanwhile, the overlying silty ice at GISP2 has elevated cosmic nuclide concentrations in it that suggest that the ice has mostly been there for the last 2.6 million years. So we sort of right now have ambiguous knowledge about the past history of the Greenland ice sheet, especially from ice core basal materials. And one thing is that precise age constraints about the timing of former ice-free events from terrestrial records has been elusive from Greenland. And there's a data bias from ice core basal materials that's actually quite important looking to the near future for climate change. And that's most of these ice cores have been collected from the interior of the ice sheet because that provides the longest ice core record and most detailed ice core record. But as we look to the future, we need to know about the margins of the ice sheet, which are the most vulnerable to warming temperatures, and if they begin to retreat, will contribute the most to sea level rise in the near future. So, Camp Century revisited. Let's talk about what we did. And again, I'll just reiterate our main finding is that northwestern Greenland supported a tundra ecosystem during at least 2 ice-free episodes in the last 3 million years or so. And for the remainder of the talk, I will walk through the lines of evidence we have for this. And that includes pore ice Delo 18 data that tells us about paleo elevation and temperature, macrofossils and leaf waxes that tell us about what actually lived on Northwest Greenland when it was ice-free, and get at the timing of these ice-free events from stratigraphy and weathering of the sediment, as well as a burial history from cosmogenic nuclides and luminescence measurements. So the basal sediment itself was redescribed by Jean-Louis Toussaint and Piache Blard a couple of years ago, and they identified that this sediment contains 2 units of diamictin separated by a sediment-rich ice layer. And for those of you who are not in the glacial geology world, diamictin is a sediment with grains of all sizes, many lithologies, often unlayered and unsorted. So a way I like to explain it to students is that it is a less tasty trail mix. It is a mixture of all sizes and types of material. And this is quite powerful for paleoclimate research because we can apply so many different analyses because we have everything to work with. Different size fractions, different minerals, and biologic remains. So it's actually a great advantage of working with diamictin. And in this pilot study, we analyzed the very uppermost part of the upper diamictin, 1059-4. And this sediment sample is more sand and gravel rich. And there was also some loose sediment with this material sort of in the jar of sample material that we used as replicate analyses. And at the very bottom of the sediment core, 1063, is a more clay-rich diamictin. And just a sort of fun aside is that when we took it out of its sample bag, we just were immediately overwhelmed with the smell of the diesel-based drilling fluid that they used when they drilled the core back in the 60s. So the first thing that we did was take off a couple of frozen fragments of the sediment for analyses that needed to be frozen. And then we thawed and extracted the melted pore ice for stable isotopes. And the more sand-rich Diamictin, the upper one, had more ice in it than the lower. And what we found is that the pore ice Delo-18 signal is enriched relative to all of the overlying ice and modern precipitation at Camp Century. The upper sample was around -23, and the lower sample was around -21.5. And if we just plot that on a old graph of the Camp Century Delo-18 profile, we see that this plots far to the right of all those values, which first glance would imply much warmer conditions. So if we just interpreted that as a temperature difference, it would be 8.5 to over 10.5 degrees C warmer than present. And that is just too warm for an ice sheet to survive at Camp Century's current elevation of nearly 1,900 meters. So we explain that enriched Delo-18 due to lower elevation and warmer temperatures. And so I'll walk through what I mean by this by just doing this cartoon explanation of how to explain a change in elevation. So right now, the section of Camp Century is around 1,900 meters. The ice thickness is almost 1,400 meters. And the bedrock elevation at the bottom is 500 meters. And of course, the Greenland ice sheet today, all of that mass is weighing down on the crust and depressing it. Similar to pressing your hand down on a Tempur-Pedic pillow, if you release your hand from it, it's going to rebound and take its original shape. So if we remove the ice sheet, glacial isostatic adjustment would raise the elevation of the underlying bedrock. And so if we have that isostatic adjustment, we remove that 1,400 meters of ice, and bedrock beneath it will rebound by about 450 meters, leading to a net elevation change of 940 meters. And that explains most of the enrichment in the Delo-18 signal. And temperatures that are anywhere between 0.2 to 3 degrees C warmer could explain the remaining enrichment. And this is all to say that the pore ice Delo-18 data requires ice-free conditions at Camp Century. So that's evidence number one for ice-free. So then, next step in this process, after extracting the pore water, we dried and wet sieved the sediment for specific analyses and tried to really save everything that we could. We didn't want to lose any of this sediment. And my first glance at actually getting to look at the sediment, it looks like weathered material. It's a weak red color. It's subangular to rounded quartz grains, mostly with a few feldspars and mafic minerals. And as we are wet sieving this sediment and looking at the rinse water, Paul Bierman turns to me in the lab at UVM and says, "Drew, look at these black specks floating in the rinse water. What is that?" And so we poured off some of these black specks, into a filter paper, and then I looked at it under a microscope, and there were fossil twigs and leaves and mosses. It was just amazing. We, were not expecting at all to find any biologic remains, certainly not so much of it. And this was just an incredibly exciting day in the lab. And I know Paul agrees that it was probably the most exciting day of science that we'll ever have. And so that was just an amazing experience. And I'm a geologist, not a plant expert. So we worked with Dorothy Petit at Vermont, and she did some identifications of these plant fossils and found that they're mostly Arctic mosses and a few fungal spores from environments that we see in Greenland and the high Arctic today. And then Elizabeth Thomas at University of Buffalo analyzed the leaf wax distributions of the sediment that we were analyzing, and she found a similar result, that it really looks like the tundra and shrubby vegetation that they find on Greenland today. And just a note that there was actually a difference in the preservation of the fossils and leaf waxes between these two different diamictins. The upper diamictin, there was more leaf wax concentrations, and the preservation of those fossils was better. It was much more fragmented in the lower diamictin. And so this really was an exciting day. And as an aside, it was only 4 days before my PhD defense, which was about nothing related to this. So it made the stress of that time in my life just go away for just a really exciting afternoon. So here, just more pictures of some of these fossils that we found. On the left are just various twigs and sedges that we found in the upper diamictin, and more detailed pictures of leaf tips from that same sample. And then the lower sample, we really didn't have as good of preservation, and mostly we found moss stems, broken moss stems. And in the last couple of months, we've been working with Barry Rock at University of New Hampshire, who is an expert in identifying woody tissue under the SEM. And he has been looking at the woody tissue that we couldn't really identify as specific plants. And he has determined that most of what he's seen is salix or Arctic willow. And he has not found any evidence of boreal forest softwoods so far. So that's amazing that we were able to find such a rich record of vegetation in this material. But we really need to know how old it is. How old is the subglacial sediment from Camp Century? So the first thing that we tried was radiocarbon dating. And we got infinite ages, meaning that this material is definitely older than 50,000 years old. Okay, so it's old stuff. So now we can use other tools by looking at the weathering and burial history of this sediment to understand its age. So we looked at the stratigraphy and the sediment weathering characteristics, as well as cosmogenic nuclides and luminescence data to determine the age of the sediment. So the upper and lower diamictins represent at least two different phases of ice-free exposure followed by burial. And the upper diamictin shows less evidence of weathering, and this is shown by much lower major ion concentrations, as well as the absence of any weathering clays on sand grains. There's also an angular contact between the upper and lower diamictins that suggests some glacial erosion or shearing. And the lower diamictin is more weathered, and it has much higher major ion pore ice concentrations and a greater abundance of weathering clays. And we also saw permafrost features like sub-horizontal ice-filled lenses in this sediment that were not observed in the upper diamictin. Okay, so that's just a relative chronology. That doesn't tell us about actual timing. So when were these sediments last exposed? So one tool that we can use are cosmogenic nuclides, beryllium-10 and aluminum-26, that are produced in quartz in the near surface. So in this extremely crude cartoon, we have cosmic rays from outer space making it through Earth's magnetic field and atmosphere that bombard Earth's surface and produce these nuclides in the upper 2 to 3 meters of surface materials. And if we have an ice sheet come along and cover that landscape, those radionuclides that were produced in that sediment are going to be buried, eroded, and transported by ice and decay away. And so we can use the decay of these two different nuclides to tell us about how long they've been buried, or sediment has been buried. So radionuclides with different half-lives, like aluminum-26 and beryllium-10, can tell us about the burial history. And this is what we call a two-isotope diagram, or a banana plot, because this thing looks like a banana. And the way that you read these is, if you have a sample that sits at the surface, it's going to accumulate cosmogenic nuclides at a constant production ratio between aluminum-26 and beryllium-10 over time, and the inventory of those nuclides is going to keep increasing. But if you then bury that sediment underneath a large ice sheet, for example, you are no longer producing those nuclides, and then they begin to radioactively decay at different rates. And as that happens, the aluminum-26 decays faster than beryllium-10, and that ratio number decreases over time. And just some important caveats, these are not absolute ages of when something was buried. They just give you a maximum duration of burial. So you could have exposure within any time within this burial age, and perhaps multiple times. So now I'll show you what the actual data looks like. And the aluminum-26 beryllium-10 ratios confirm that the upper and lower diamictins have different burial histories. If we look at the upper sediment, we have a aluminum-beryllium ratio of about 4.5, which corresponds to burial for no more than 1.0 plus or minus 0.1 million years. The lower sediment, 1063, that aluminum-beryllium ratio is much lower, 1.8 plus or minus 0.4, which corresponds to much longer burial, but no more than 3.2 plus or minus 0.4 million years. And this is, again, reiterating, we have at least two ice-free periods at very different times, once within the last million years and a much older one within the last 3 million years. So that's burial dating method number one. The next method that we can use is luminescence, and that allows us to answer the question, when was this sediment last exposed to sunlight? So I will try and walk through how this method works. Again, my expertise has more to do with cosmogenic nuclides, but I'm going to do my best to explain luminescence. So when material is buried beneath Earth's surface, the background radiation, low-level radiation from other Earth materials, releases ionizing radiation that excites electrons in that material, which then fill in little holes in crystal lattices of minerals like quartz or feldspar. And so over time, it builds up a signal, a luminescent signal. And that can accumulate over hundreds of thousands to up to 1 million years before it becomes saturated. But if that material is unburied and exposed to sunlight, it becomes bleached. Bleaching, just like in a washing machine, it's going to release that stuff out into the environment. So you lose all of those excited electrons that had accumulated over time. And that happens very quickly. But then something could be buried again. So for example, you have sediment that was on a landscape that is now buried beneath an ice sheet. And those electrons begin to accumulate again inside of the holes in the crystal lattice. And your luminescence signal accumulates over time. So now a geologist or two comes along and collects that sample in the dark. You absolutely cannot expose this stuff to sunlight at all. And you measure the background radiation or dose rate of the material in that sample. And then you slowly dose the material with infrared or blue-green light to slowly bleach those minerals and release those electrons that you can measure. And you measure the equivalent dose of radiation by bleaching that out. And you can use that information, that equivalent dose of what you expose the sediment to in the lab, and divide it by the dose rate or the background radiation to understand an age. Okay. So luminescence and beryllium-10 together allow us to really refine the burial history of these sediments. And Tammy Rittenauer at Utah State has been spearheading the luminescence measurements on this material. And I'll start at the bottom with aluminum-26. Beryllium-10, remember, it's no older than 3.2 million years. And the infrared luminescence data from this sediment suggests it was last exposed to sunlight more than 0.7 million years ago, but more likely much earlier, before 1.4 million years ago. And then in the upper Diamictin, our aluminum beryllium maximum burial age is less than 1 million years. And just in the last few weeks, Tammy has finalized some IRSL measurements from the upper Diamictin and got two dates from 2 different grain sizes of feldspar of 374 and 388,000 years. And we'll talk about the significance of that new data in a bit, but let's put everything in context, these ages of the sediment. So the Camp Century lower Diamictin is possibly correlative with the earliest advance of the Greenland ice sheet, because beginning about 2.6 million years ago, the Greenland ice sheet reached sort of its, present fully expanded size. And we know from offshore geophysics that there have been multiple shelf edge advances since that time. So perhaps that lower Diamictin is from one of the earliest advances of the Greenland ice sheet. And now that we have, knowledge about the age of the sediment and the actual macrofossils and biomarkers in the Camp Century Diamictins, it's becoming more apparent that Greenland was greener, definitely during the Pliocene and perhaps during multiple Pleistocene interglacials. And so that corresponds with pollen data offshore, as well as rare terrestrial deposits in ice-free areas that have fossils in them. And so as we think forward about this, are these ancient ecosystems beneath the ice sheet omens for a greener Greenland in the future? Will we see tundra in northwestern Greenland again, and perhaps boreal forest in southern Greenland, similar to the forest DNA that they found in Dye 3? And then the next question is about the stability of the Greenland ice sheet. And it's becoming apparent that the Greenland ice sheet has melted and reformed at least once in the last million years. And this doesn't mean that there could have been small remnant ice caps in the eastern highlands, but large portions of the ice sheet appear to have melted away in the last million years. And all of the ice core basal materials have ages that are less than 1 million years. So GRIP, GISP2 both have maximum ages of about 1 million years, and that corresponds with Camp Century as well as Dye 3. So within the last 1 million years, one comparison between ice core basal materials that I want to focus in on is between Camp Century's upper Diamictin and the subglacial bedrock at GISP2. And if we look at the aluminum beryllium ratios, which tell us about the burial history of these surfaces, they are very similar. And this really reinforces that the ice cover history between the ice margin at Camp Century and GISP2 in the center of the ice sheet appear to be quite similar. And this has important implications. One way to look at this that is important is that the Greenland ice sheet has survived most Pleistocene interglacials, while all of the other northern hemisphere ice sheets vanished. So in some ways, we can think of the Greenland ice sheet as being quite resilient. But it appears that much of the ice sheet has disappeared and reformed at least once in the last 1 million years. And so the resiliency of that ice sheet has a natural limit that was crossed in the past. And now we think we know when, at least at Camp Century. The upper Diamictin luminescent ages correspond to the end of the MIS 11 interglacial. So MIS 11 was a long interglacial between 374 to 424,000 years ago. It's marked by very high sea level, 6 to 13 meters above present, carbon dioxide around 285, and in the Eastern Arctic in Siberia, it was the warmest period of the last 2.6 million years, and that's known from the Lake E sediment core. And we also had prolonged warm sea surface temperatures off of southern Greenland, and pollen records from marine sediment show that there was likely boreal forest covering southern Greenland at that time as well. So if we then focus in just within this time frame at these IRSL ages and how they match up with these different paleoclimate records, it appears that the luminescence age records a readvance of the Greenland ice sheet in northwest Greenland at the end of MIS 11. These IRSL ages postdate the warmest interval of MIS 11, substage 11C, that's marked globally by the Benthic-Dalloway team stack, as well as global mean sea level and Arctic temperatures and sea surface temperatures off of southern Greenland, and also the highest pollen concentrations off of southern Greenland. And then another interesting correlation here is that ice-rafted debris, beryllium-10, which tracks how landscapes are being eroded and transported out into the ocean, we see a slight uptick in beryllium-10 offshore of northwestern Greenland, which could correspond to the erosion of that formerly ice-free landscape by the readvance of the ice sheet during MIS 10, that glacial period. And so the implication here is that from the Camp Century upper Diamictin, we have direct terrestrial evidence for a smaller Greenland ice sheet during MIS 11. And we can use these IRSL ages, the luminescence ages, with our existing cosmogenic nuclide burial ages to actually determine how long this ice-free event was. And what I will do now is walk you through another banana plot or a two isotope diagram showing how we did this. So today, when we measured the cosmogenic nuclide ratio in the upper Diamictin, it had a ratio of 4.4 plus or minus 0.1, and that corresponds to a burial age of no more than 1 million years. But if you correct that burial age for 388 or 374,000 years from the IRSL ages, we then move up on this two isotope diagram. And we see at the end of MIS 11, that ratio was higher, around 5.3. The next thing that we did was determine a variety of scenarios of how long that sediment could have been exposed to achieve that ratio. And you cannot expose the sediment any longer than about 13,000 years. Otherwise, you get inherited ratios that don't make sense. So that limits the exposure of whatever sediment came in at the beginning to being buried for a much longer period of time. And this is all to say that the ice-free conditions during MIS 11 at Camp Century were no longer than 13.4 thousand years. And this allows us to answer a really important question about MIS 11, and that's how much of the ice sheet melted to allow Camp Century to be ice-free for 13.4 thousand years. And this is really preliminary data that Benjamin Kiesling at Vermont has been working on. But his preliminary modeling suggests that in order to keep Camp Century ice-free for that duration of time, there's a minimum contribution of at least 1.7 to 2.3 meters of sea level from Greenland. And that it could be more. That's just to expose Camp Century. But if it was a smaller ice sheet, obviously the contribution of sea level rise from Greenland could be more. And really, this is the first direct terrestrial evidence from Greenland that can be used to audit the high sea level budget of MIS 11. So this is just a very interesting thing that that we've been able to get out of such a small amount of sediment. And so I'll summarize now that some of the main findings from our pilot study is that as we look at Camp Century subglacial sediment, as well as other materials from the bottom of ice cores around Greenland, is that there is evidence of ancient ecosystems preserved underneath the ice sheet. And at Camp Century, we found 2 ice-free events, one in the early Pleistocene and again within the last 1 million years, with direct terrestrial evidence for a smaller Greenland ice sheet during MIS 11. And keep in mind that we still have over 3 meters of sediment to examine, so there's a lot more data to come. And then just to zoom out one more time to the big picture, the Greenland ice sheet was resilient during most of the Pleistocene and survived most of the Pleistocene interglacials. But that resiliency had a natural limit, and the Greenland ice sheet melted to a much smaller state, or perhaps absent, in the absence of human influence. And while the forcing factors that caused those deglaciations in the past were different, or maybe different than what we face in the future, you know, we have to ask, what will happen as humans climb higher on this ladder of CO2? And if we go back to MIS 11, the last time Camp Century was ice-free, we were only at 285 parts per million. And by the time that the U.S. Army had built Camp Century in the 60s, we were above what had been observed in the geologic record of the last 800,000 years. And now we've marched up to 415 parts per million. So with that, I'm happy to take any questions. And thanks so much for attending my talk tonight.
Thank you very much indeed. Are there any questions for anyone? So we've got one from Adam Kashtan in the chat. Do you want to unmute yourself and ask that, Adam?
Yes, it's my question about Diamictin. You have an up level, a low level of Diamictin. What on different facial vegetation? What
Yeah,
different organic?
So the differences that we can, I mean, the main difference is the preservation. The upper Diamictin is better preserved fossil-wise than lower Diamictin. But the lower Diamictin, there was a greater abundance of mosses. We haven't done the full characterization of that material yet. So we don't know if it's completely different. One thing that we are working on right now is DNA analysis of both of these sediments, which will give us, you know, the full suite of what's there. I don't know if the lower Diamictin it'll be possible to go back that far in time, yeah. But it appears that both are tundra plants, but one is just more rich in moss fragments.
Yeah, thank you, Andrew. Great talk. Great talk.
Thanks, Adam. Appreciate it.
And we have a question from Yarrow Axford.
Okay.
Hi, thanks so much for the great talk. And I'm just increasingly terrified of MIS 11. Thank you. Could you summarize the evidence that upper Diamictin records the last time that Camp Century was ice-free versus a scenario with a variable ice margin where there were other retractions of that margin, but the evidence for them is perhaps gone? It's a great point.
So the evidence that in the upper Diamictin that it was ice-free, just in general, just the several. Sorry, I misunderstood.
Sorry, I guess my question is, what's the evidence that Camp Century has been covered by ice since probably MIS 11.
Right. Okay. Now I understand. Okay. So the first thing is actually just the luminescence measurements is probably the most diagnostic, because if it's exposed to any amount of sunlight for a very short amount of time, that luminescence signal will be lost. And so that I think is our main line of evidence that it has not been smaller since that time. It's been ice covered since that event. I think that's probably the best evidence for it right now. But I'll also know that IRSL data is pretty new, so you know, we still need to think through some of it.
Well, thank you.
Yeah, thank you so much.
Are there any other questions for Drew?
Yeah.
Let me just check on Facebook. Lots and lots of thank yous there from everyone.
Thank you all.
Just check on Facebook. No, it looks like, oh, Roger, go for it. Roger
Thanks very
Clark.
much, Davey, and thanks, Drew. That was fascinating. It's a bit of a tangential question, but especially given the theme of what you've just described to us, do you know of any plans to make any more physical measurements on that last 3.5 meters, density, and any kind of geophysical properties? I know that there's been some fantastic GPR work over over Camp Century, and whether anything from that ice bed sediments might be useful for calibrating radar reflectivity or even seismic.
Oh, that is a great question, and that's not something that I'd considered. It was about interfacing between the ice sheet geophysics people and the properties of the sediment. We have done some density measurements. Piash Blard did density measurements in the lab a couple summers ago, but we haven't considered how that might be integrated into the radar community. But thanks for that idea.
And Pierre-Henri, do you want to make your comment?
Oh no, thank you. Drew answered very well. I agree with him that the best chronological constraint for MIS 11 last advance is the OSL age. Yeah, I totally agree with him. But I just added some few answers about this. Yeah, and we did the density measurement. It's very clear that the what we call the ice wedge between the two Diamictin is close to 1. The density is clearly ice-free, almost ice-free material. And the average density of the Diamictin is about 2, between 2 and 2.2.
Thanks, Pierre. Gosh.
Mike Bentley.
I see it. So did you sample IRSL from the center of sediment because presumably margins were exposed to light? So yes. Piash and Jean-Louis sampled the upper Diamictin in red light, so in the dark, in the freezer room in Copenhagen, and then wrapped it in aluminum foil, and they got about what was it, like 3 centimeter cube sized, I think that's what it was, and wrapped it in aluminum foil and then sent it to Tammy, and then she was able to ensure that it was not exposed to light as she got individual grains that were at the core of that sample.
Brilliant, thank you. Any last, sorry, there's a lot of comments flying around. Yeah, I think we're probably finished with questions unless Yarrow, you want to unmute and make that comment. Mary Berglin.
Yes, can you guys hear me?
Yes, we can.
Perfect. I was just wondering if you had looked at the ice/debris concentration in the ice core, because from those pictures, it looks like you have had some sort of sublimating surface of the ice core. So I was just curious if you had done those calculations.
Right. So I mean, when I was processing these sediments, I did it by mass first, and I don't know that number off the top of my head, but I have it. And so that the percent ice in the upper Diamictin was almost 16%, and the lower Diamictin was about 5%. There was not, we did not get very much water out of these samples to work with. But does that answer your question, Marie?
Yeah, it does. I was just looking at the Oak Valley ice core that we've been drilling into, and I was just kind of comparing with what the concentration difference are between those, which is quite interesting.
Was the Oak Valley much
well, we get
ice rich?
Yeah, so we have a section in the middle of the ice core that is about 0.9 debris concentration, but roughly it averages out to be less than 50. But we do have like some extreme high debris concentrations, almost cemented debris in the center of the ice core.
Mm-hmm. And those
I was kind of curious.
Layers.
Yeah.
Okay. Interesting.
Cool.
Yeah. Always fun to see what sediment comes up the bottom of these things, right?
Oh yeah. Nice.
Okay, fantastic. I think we've run out of questions there. So just falls on me to say an enormous thank you again to Drew for such a fantastic talk. And to also say that the next seminar, it's actually 2 weeks from now. So we've got 1 week's holiday next week. And in 2 weeks' time, we have Joseph Grayley from Northumbria University talking. So we'll see you on April the 14th for the next seminar. And thank you very much indeed, Drew.
Oh, thank you so much for having me. It was a pleasure. Thank you.
Lots of thanks coming there on the chat.
Oh. Thank you all.
Yeah, bye to everyone, and thank you very much again, Drew.
All right, thanks all.